So I've switched to pen and paper. The example I'm going to work is of a ball thrown with speed 10 meter per second at angle 30 degrees above the horizontal from a 30-meter cliff. Question is, how long does it take to fall? So how long means I'm looking for a time, right? I might as well identify what all of this is. The ball is thrown with this speed, so this is the initial speed, right? The v. The angle 30 degrees from above the horizontal from a 30-meter cliff. So actually, I'll draw the picture first, but before I decide what the 30 meters is. So here's my picture. It's a cliff, so like this, and the ball is thrown 30 degrees above the horizontal, meaning that this angle is 30 degrees. And it's thrown at 10 meters per second, so the speed v sub naught. I guess I should call this the initial speed, right? V sub naught. The initial speed is the 10 meters per second. And it's from a 30-meter cliff. In other words, this height here is 30 meters. I'll put it in. And now the part about drawing the axes comes into play, because I need to make a choice. I need to make a choice of where y is going to equal 0. So first of all, I'm going to choose the horizontal direction to be x and the vertical direction to be y. I need to choose where the origin is. So there are two heights where it would make sense to put the origin, either at the top of the cliff, so that the initial height was 0, or at the bottom of the cliff, so that the final height was 0, because the ball is going to follow a trajectory like this and eventually hit the ground. So I can choose y equals 0 anywhere, but the two convenient places are either at the top of the cliff or at the bottom. And so I'm going to choose y equals 0 at the bottom. It's really prejudiced to think of the bottom of the cliff as 0 height any more than the top of the cliff, but it's convenient for me to think of it that way. So anyway, I'll call this point my origin. So here's x, and here's y. And in other words, the initial height is 30 meters. And the final height is 0. Okay. Now, I want to find out how much time it takes to fall. And so I'm going to look at my 6 equations. And I'm going to think for a minute. Okay, I spent a minute thinking and really remembering, because I've done this problem many times. First of all, to find out how long it takes to fall, I don't need the x equations at all, right? The falling is happening entirely in the y direction. And there are two ways I can proceed. One is to solve the first equation in y for the time. The way I would do that is, in fact, I'll set up the equations both ways. So method 1, in fact, I'm going to solve the other way. So I'll call this method 2. Method 2 would be to write down y is y sub naught plus v sub naught y t plus 1/2 ay t squared. And by the way, on the picture, if you want to if you want to illustrate that the acceleration is the acceleration of gravity, you might say that the acceleration is like this, and that the magnitude is g. So one way to write it. Okay, so in this equation, the final y is 0, right? Because the ball, the ball falls until it hits the ground, and I want to find out how long that takes. So the final height is 0. The initial height, because I chose the bottom to be 0, the initial height is 30 meters. So y sub naught is 30 meters. Plus the initial velocity is the 10 meter per second. In fact, let me blow this up a little bit. So here's x, here's y, here's the initial velocity, here's the 30 degrees. And so the initial velocity in the y direction is the y component of the initial velocity. So the y direction is up and down, which is opposite the angle. Or you can think the x direction is adjacent to the angle, right? So the x direction gets the cosine, the y direction gets the other one, the sine. So it's going to be the magnitude v sub naught times sine of 30 degrees. And notice that it's plus because v sub naught points up and to the right. So v sub naught is in the plus y direction. And then plus 1/2 ay is g, which is the 9.8 meter per second squared, in the negative y direction, right? So the acceleration of gravity is down. The magnitude of the acceleration is g, so the y component is minus g. The minus solely because I chose y to be positive up and the acceleration points down. And that's times t squared. And so, whoops, I forgot to write the t here. Right, this is v sub naught y times t. V sub naught sine 30 is v sub naught y times t. So this is nice. It's a quadratic equation. The way you would solve it, in fact, I'll just quickly write this down. The way you would solve it is you'd say the time is equal to, actually, I'll hold off on this until later. It's a good example of using the quadratic formula, but I just wanted to set up the equation at this stage. The method I'm going to use, so the idea here is that we could solve this. We can solve this to find t, because t is the only thing we don't know in this equation. We know v sub naught and we know g. It's the 9.8 meter per second squared acceleration of gravity near the surface of the Earth. So method 1, though, you have 2 other equations, right? This one and this one. And what I can do is I can solve the third equation for the final velocity, the y component of the final velocity, vy. And then I can use the second equation to solve for t. The reason I can do that is that I'll know all of the variables in each of the equations except the thing I'm solving for. Vy from the third equation and then t from the second. So let me show you how that works. So first of all, in order to solve the second equation, I have to get vy first. So I write the third equation, which is vy squared is v sub naught y squared plus 2a sub y delta y, or actually I'll write y minus y sub naught. And so to get vy, I take the square root of both sides. So this is equal to square root of v sub naught y squared plus 2ay y minus y sub naught. And I'll might as well solve for the number just to make it easier. So v sub naught y is the, remember I figured out it's v sub naught times sine 30 degrees. So v sub naught y is v sub naught sine 30 degrees, and that's squared, plus 2. Ay is the minus 9.8 meter per second squared, times y minus y sub naught. Remember y, the final y is 0, and y sub naught, the initial y, is the 30, where it started. So we've got 0 minus 30 meters. I'll draw that to separate these. And so if I plug in numbers, I get square root of v sub naught is the 10 meter per second times sine 30 degrees, and that's squared, plus all of this, 2 times minus 9.8 meter per second squared times minus 30 meters. And I'll pause for a second to calculate that. I got 24.76 meters per second, and that's reasonable. I mean, it's bigger than the 10 meter per second. I'm sorry, it's bigger than the 5 meters per second, which was the initial y component of velocity. 10 meters per second times sine of 30 degrees is 10 times a half, is 5 meter per second. So it's bigger than the initial y component of velocity. It's bigger in magnitude, which makes sense because the ball went up, but then it fell past where it started and continued to fall. So you'd expect the y component to have to be larger in magnitude at the ends than at the beginning. So that's Vy, and then I have the simple equation, equation 2, that I can solve for the time. So I write down Vy is equal to v sub naught y plus ayt. So to solve for the time, I subtract v sub naught y from both sides, and I get Vy minus v sub naught y is equal to ayt. I divide by ay on both sides, and I get that the time, notice that I'm calling the initial time time 0. That's what we do with these equations. And so the final time is how long it takes to fall. So t is equal to Vy minus v sub naught y over ay. And Vy is the, okay. Quick point here. So Vy squared was equal to all of this. So when I took the square root, Vy was either plus or minus this, right? Because the square root can be either positive or negative. And in fact, Vy is negative because when it hits the ground, it's going down in the minus y direction. So Vy turns out to be minus 24.76 meter per second. Also notice I kept an extra digit here because I want to minimize rounding error. Later I'll round to 3 digits in accord with the 3 digits I started with in the information. All right, so Vy is minus 24.76 meter per second. V sub naught y is the 10 meter per second times sine of 30 degrees, and is minus v sub naught y, so minus the positive value of v sub naught y, divided by ay, which is minus 9.8 meter per second squared. And I'll pause and calculate. And I wind up with 3.04 seconds. So, and that's reasonable, right? Because, you know, you throw something and it falls about 100 feet, a bit more than 100 feet. 3 seconds sounds reasonable. So, I mean, it's not like 5 years or, you know, a millisecond. So, I'm going to show how to solve using the quadratic equation via method 2. If you're interested in seeing that, please keep watching. Otherwise, I'm going to ask everyone to try to calculate where the ball lands using the information you just calculated, the time it takes to fall. So the question is, where does the ball land? So you have 2 options. Either pause here and find where the ball lands immediately, or if you're interested, watch me solve using the quadratic formula and then find where the ball lands. And then everyone join me at the end, at which time I'll solve this part. Okay. So method 2 with the quadratic formula. I want to remind you that if you have an equation of the form ax squared plus bx plus c equals 0, the quadratic formula says that x is minus b plus or minus square root of b squared minus 4ac over 2a. And you can derive that. It's done in your math classes. So it's a useful formula to memorize. But I won't expect you to memorize it for this class. I'll put it on the formula sheet. And if it's not there, ask me for it. So I'm going to use this formula to solve for t from this equation. So it's purely a matter of identifying which number is, or variables constitute A, which constitute B, and which constitute C, and then plugging into the formula. So T is equal to minus B. So B is the thing that multiplies your variable to the first power. Up here, I'm solving for T, not X. So T is my variable. Up here, the thing that multiplies t to the first power is v sub naught sine 30 degrees. So b is v sub naught sine 30 degrees. And then I have, I'm going to have to spread out here. That's not enough room. Okay. Let me do this. Okay. So yeah, t is minus b. So b is the thing that multiplies the variable to the first power. That's v sub naught sine 30 degrees because it multiplies t to the first power. So I've got minus v sub naught sine 30 degrees plus or minus, again b, but squared this time. So v sub naught sine 30 degrees squared minus 4 times a. A is the thing that multiplies the variable to the second power. The variable is t. That's what I'm solving for. So what multiplies the variable to the second power is minus g over 2. So I plug in minus g over 2. And that's times c. C is the thing that multiplies the variable to the 0 power. In other words, variable to the 0 power is 1. So c is the thing that's alone. It's not multiplying any power of the variable that you can see, right? T to the 0 is just 1. So it's c times 1. And the thing that's not multiplying any visible power of the variable is the 30 meters. So 30 meters. Okay, and divide by, divide by 2a. Again, a is the 1/2 times minus g, so 2 times 1/2 times minus g. Okay, and I'll plug in. Minus v sub naught is the 10 meter per second, and it comes out to be 10 meter per second times sine 30 degrees is just 5 meters per second. So you could always simplify that before writing all of this out. So 10 meter per second times sine, times sine 30 degrees squared, and minus 4. So minus times minus is plus. 4 divided by 2 is 2. So it's going to be plus 2 times g, 9.8 meter per second squared, times 30 meters. Whole thing over. 2 times 1/2 is 1, times minus g is minus 9.8 meter per second squared. And I'm going to pause and calculate. So I came up with two numbers, 3.04 seconds and negative 2.02 seconds. You'll notice that they're scribbled over because I made a mistake plugging into my calculator. Even if you've been doing this for decades, several decades, these things still happen. And notice that one answer corresponds to this minus 5 meter per second plus this divided by negative 9.8. That's the negative 2.02 seconds one. The other one corresponds to minus 5 minus this divided by negative 9.8. That's the positive one. Now, the negative value of time isn't necessarily excluded. I mean, negative time just indicates it's a time before whatever time you decided to call 0. But here, the time we decided to call 0 is the time at which the ball was thrown. And so a negative value of the final time indicates that the ball landed before it was thrown. So that doesn't make sense. So the time is the 3.04 seconds, and this is the time at which the ball hits the ground. The time at which the ball was thrown was 0, and so the time at which the ball hits the ground is also the amount of time it took for the ball to fall. So we had 3.04 seconds, which is the same as we had before, 3.04 seconds. So it's good. I mean, both methods give the same answer, which they have to because they're both based on the same physical situation, of course, and the equations were consistent with one another. In fact, the third equation was derived from the first two, and the first two followed the same logic in their. The same logic was used to derive both of the first two equations. Okay, and then the problem to try. So if you haven't tried it yet, please try it. And otherwise, welcome back. So the problem is, where does the ball land? And since I have some room here and it's a short problem, I'll just say the try is where does the ball land? And if we look at the picture, well, the ball lands at whatever the final value of x is. right? It starts at 0 and it lands here, and we're not finding the distance. Rather, we're just finding where it lands. So, but we can talk about this position as being numerically equal to the distance from the base of the cliff, which is really what we want to say. We want to say how far it lands from the base of the cliff, not the value of x in some set of coordinates I chose. Okay, it's the same thing, but we want to say it in terms of something that means something to everyone. Everyone can agree on where the cliff is. All right, so here's my picture. I want to find the value of x where the ball lands is the final value of x. I'm going to use one of these equations that involve x because I want to find a value of x. The second equation does not have x. I mean, it has subscripts x, but it doesn't have the variable x. So I can't use the second equation. At least if I'm going to solve with just one equation, it can't be the second one. Third one, I don't, let's see, well, the third one, oh, here's the problem with the third one. The acceleration in the x direction is 0, right? All of the acceleration was in the y direction. So the acceleration has a y component, but no x component, or the x component is 0. So with 0 x component of acceleration, this whole thing is 0. So when you take away this whole thing, x no longer appears as a variable in the equation, and so I can't use the third equation to solve for x. First equation, I can use, it has x, and I know everything else, which I'll show in just a second. So my equation is x equals x sub naught plus v sub naught xt plus 1/2 a sub x t squared. My x sub naught is the initial value of x. The initial value of x, the x at time 0 was 0 because I called the base of the cliff the origin. So the ball started at x equals 0. X equals 0 and y equals 30 meters is the location of this point. So x sub naught is 0 plus v sub naught x t. So v sub naught x, it's the magnitude of v sub naught times, it's the x component of v sub naught. So we have the two questions, right? First of all, is the x component positive or negative? Well, v sub naught points in the positive x direction. It points to the right. So it's going to be plus the magnitude, v sub naught, times either cosine or sine. Well, the x direction is adjacent to the 30-degree angle. So we say cosine of 30 degrees. Remember that was our mnemonic. If the angle is adjacent to the direction, the component of which you're finding, or the component in which you're finding, you use cosine. And times t, and then plus 1/2 a sub x. Well, a sub x is 0. The only acceleration is due to gravity. So and gravity acts down. So none of gravity's acceleration is in the x direction. Times t squared. And so you wind up with just v sub naught cosine 30 degrees times t, because this is all 0. And so you plug in v sub naught was the 10 meter per second times cosine 30 degrees times the time when the ball hits, which is 3.04 seconds. And so I'll pause and calculate. So it comes out to be 26.3, and notice the units, meter per second times seconds. The seconds cancel, you get meters, which you should because it's a position x. And so the final position x is 26.3 meters. So I would accept just 26.3 meters. It's a little bit better to say 26, where the ball lands is 26.3 meters from the base of the cliff, because that way everyone knows what you're talking about. And that's the answer because I chose the origin to be at the base of the cliff, and so a value of x of 26.3 meters is the same as 26.3 meters from the base of the cliff. All right, well, I hope that this has been useful, and any questions, contact me, please. I hope you have a very good rest of your day.